Hi everyone, this is the third video on section 14.4, the normal distribution, and in this video we're going to go through some application problems using the normal distribution. In our first example, we're told that to qualify for a management training program that's offered by your employer, you have to score in the top 10% of all the employees that take a standardized test. Now we're going to assume the distribution of scores is normal, and that when you received a score of 72 on that test, all the other people that have taken it have a mean of 65, standard deviation of 4. Clearly, you did better than average, but are you in the top 10% of all of the employees that take the standardized test? Okay, and then what the question says is, what percent of those who took this test had a score that is below yours? And what I want to do first is take a look at our normal distribution kind of setup for this problem, and then we'll go through the steps to answer it. All right, so I'm going to draw my horizontal line here, and then my bell curve normal distribution above it. That looks okay. All right, so that we're told that the mean, which goes in the middle, is 65, and the standard deviation is 4, and somewhere off to the right of the mean, I have a score of, or you have a score of 72 on the test. That 72 represents your score, okay? So what we want to know is that good enough to be in the top 10% of all the people that take this standardized test? And we do that first by finding the z-score. So we're going to write down the formula. Z equals x minus mu over sigma. X is my data point, in this case my test score or your test score. Mu is the mean, sigma is the standard deviation. All right, so x, my score, 72, minus mu, the mean, is 65, divided by 4. 72 minus 65 is 7, over 4 is 1.75 when you type that into your calculator. Now you can see that our z table just was added on to the screen here. So let me pan on down to that, and I need to look up a z-score of 1.75. So let's zoom in on that. Here we go. And I'll get my highlighter out. Here's 1.7. Whoops, there's 1.7 right there. And here's the 0.05 place. That color looks terrible. There we go, 1.75. And those two meet right here at 0.4599. Okay, so 0.4599 is the area. All right, so let me pan back up and zoom out a bit. 0.4599. Zoom out a little more. There we go. All right, so let me write it down, then we'll talk about what it means. The area that corresponds to that z-score is 0.4599. Now I'm going to look back at my bell curve. Let's interpret this. What does that mean? Well, if you were paying attention in the last video and did your homework, that means that the area, the amount of stuff between the mean and my score, is about 46%. That stuff in there is 0.4599. The question is, does that put me in the top 10% of all the test takers? Okay, well, the way that we answer that is to take all the stuff that's to the left of 65, and I don't need to look that up because I know that 65 is the mean, which is in the middle. So the area of all the stuff over there, all the test takers in this case, 50% of the test takers score below a 65 on this test, 0.50. All right, and then if we add 0.50 plus 0.4599, that is equal to 0.9599. And if you subtract that from 100%, 1.00 minus 0.9599, you will get 0.0401. And so that says that only 4%, that is approximately 4%, only 4% of the people taking that test scored better than me. So am I in the top 10%? Yes, absolutely. Yes. Sorry, let me write 72 is in the top 10%. 10% of test takers. All right, so that's what the workflow of this problem looks like. Draw your bell curve, draw it out by hand, shade, label things, what's in the middle, the mean's in the middle. Where is my score? My score was a 72, okay? And then convert that your test score to a z-score, find the area that corresponds to that, and then how do I answer the question? Am I looking for the amount that are above that, the amount that are below that? That's how we work through this problem, all right? All right, in our next example, we're comparing baseball players from two different eras. So we have Ty Cobb was a baseball player in 1911, in the 1910s, really, and then Ted Williams, he's another baseball player, played in the 40s. I'm not sure if it was the 30s and 40s, but played in a different era. Baseball was different in those two times. Baseball looks different now if you were to look at a baseball player nowadays, okay? And Ty Cobb, he had a batting average of 4.420. Ted Williams 0.406, and in order to compare them against each other, we need to standardize those two batting average. Clearly, Ty Cobb had a better batting average, but because he played in a different era, was it actually better? So to compare them relatively to each other, we use z-scores. All right, so we're going to get a z-score for Ty Cobb, and we're going to get a z-score for Ted Williams. All right, so I'm going to zoom out a little bit here, and we'll go and find these two z-scores. All right, and we'll start with Ty Cobb. Ty Cobb. All right, and we need his z-score. Z equals x minus mu over sigma. So Ty Cobb's batting average, 0.420. That's the x, the data point, minus mu, the mean. For Ty Cobb, we're going to use the 1910s, and the mean batting average was 0.266. And the standard deviation was that decimal 0.0371. And so we'll type that into our calculator in just a minute, see what we get. But we'll do the same thing now for Ted Williams. Z equals, I'm not going to write x minus mu over sigma again, I just did. Ted Williams' batting average, 0.406, minus the mean in Ted Williams' era of the 1940s was 0.267. 0.267, and then his so the standard deviation in the 40s was decimal point 0.0326. Now let's get our calculator, type it in, and see what we get for both players. So first for Ted Williams, I got a z-score of 4.15, so that's over 4 standard deviations above the mean. And then for Ted Williams, I got a z-score in my calculator of 4.26. So he is also over 4 standard deviations above the mean, but his is still higher. So which batter was ranked higher in relationship to his contemporaries, means like the other people that were playing in his era? It would certainly be Ted Williams. Ted Williams had the better batting average. The better relative batting average. There we go. All right, so that's the answer to that example. All right, so this last example in the section is kind of interesting, all right? So take a second, read through it if you want to pause the video. The important parts as you read through is that the mean failure time for these Samsung TVs is 3,000 hours. On average, they fail after 3,000 hours. And the standard deviation is 500 hours. This will be done, while Samsung is producing and testing things at their plant. This is the data that they collect after having the TVs on, because they collect data on their own products. Right? They want to do that. All right, so it says, assume the typical purchaser will use the TV for 6 hours per day. If the manufacturer does not want more than 5% to be returned as defective within the warranty period, how long should the warranty be? So we're saying we've collected this information. How long do I need to set the warranty for so that most of the TVs, 95% of them, will last until the warranty is due? Kind of an interesting thing to think about. All right, and the idea is we want a z-score so that at least 95% of the area is beyond that point, right? So 95% is, as it says, occurring after this point right here on my bell curve, right? 5 from 100 is 95. So we want the z-score such that 95% of the area is below that score. All right, since we know half of the area lies below the mean, our problem, as it says, reduces to finding a z-score greater than 0 so that 45% of the area lies between the mean and that z-score. So if the area is 0.45, as it says right here, we can use the table from a little bit earlier in this video. Go ahead and pause and back up if you want to. If the area is 0.45, then the z-score is 1.645. Okay, 95% of the area underneath the standard normal curve falls below z equals 1.645. Similarly, by symmetry, 95% fall above negative 1.645. Okay, 95% is below the positive one, 95% is above the negative one. Then we're going to set up our z-score formula to be negative 1.645 equals x minus 3,000 over 500. And that I can do a little bit of algebra and solve for x. So we're kind of going backwards through this problem. We're going to multiply by 500 instead of dividing like we do when we find the z-score. That multiplies to give us negative 822.5 is equal to x minus 3,000, and then we add 3,000 to both sides, so plus 3,000 in my calculator, gives me an x equal to 2177, so 2,177.5 is equal to x. Okay, so when we solve for the number of hours, we get 2,177 hours. That's how long Samsung needs those the warranty to be, so that only a few of the televisions will be covered once they break. Now the final steps to this problem, we're going to take that 2177.5, that number, and divide it by 6, because if you recall, that's how many hours a day they were watching TV. So that number divided by 6 is equal to 362.9, etc., and then some other numbers, hours. No, excuse me, that 362 is days. 362 days. The 2,000 number, that was hours. 2,000 hours, or 362 days, which, notice that number is about a year. Right? So if Samsung sets the warranty to be 1 year, then only 5% of the televisions are going to break within that 1 year time period. All right? Most of them, 95% of them, will make it longer than a year. All right? So that is the end of the video. That's the end of this section. Please let me know if you have any questions, especially on this last problem. Thank you very much for listening, and have a wonderful day.